Good morning, good afternoon, good evening, everyone. It's my great pleasure to introduce you the third keynote speaker, Dr. Bruce Max. Dr. Max is a professor, is a PM, wider professor of computer science at Duke University, and currently he's on leave at Emerald Innovations as the director of engineering. Before he joined the Duke, he spent 15 years at CMU and as the assistant professor, associate professor, and a full professor. During his tenure at CMU, he also got time to have founded InHome. And many of us know him as a system builder. And the InHome content delivery network also received the SIGCOMM Networking System Award, which is a very prestigious award. And like I said, many of us know that Professor Max is a system builder, but fewer probably know him actually is also a theoretician. And as far as I know, when he studied his study at the MIT for his bachelor's to PhD, he actually majored in algorithms. Sometimes I wonder if this is his secret to be so successful in both industry and academia. Today he is going to share with us his work at Emerald Innovations on the health monitoring. So without further ado, Dr. Max, the floor is yours.
Thank you, Sungching. Thank you for the very kind introduction. And thank you for inviting me to speak here. It's really an honor. With the only drawback that the conference is falling during my vacation in Hawaii. So my audience will be hopefully treated to a Hawaiian sunrise behind me sometime during my talk. It's early in the morning here. I know my title doesn't sound like the kind of topic you would normally expect to hear about at ICDCS, but I hope to raise a few interesting distributed computing issues during this talk. But let me just dive in and tell you what we're doing. This is a picture of an office at MIT, and on the wall circled in green is an Emerald device. And I like to call this a human radar device. It was developed by Professor Dina Katabi and her research group at MIT, and now Emerald Innovations has been spun off to commercialize this technology. You mount this device on the wall, and it uses a form of radar to track the movements of people in the room, even through walls. And in addition to tracking their movements, it can also record other biometrics, which we'll see in a moment. This is an early demonstration of the ability of the device to track the movement of a person walking around in a room. This is one of Dina's former students, Fadil Adib, who's now joined the faculty at MIT. And so this was in this particular example, the device itself is not even in the room; it's on the other side of the wall. But it can track him to within a few centimeters as he walks around the room. The technology has advanced quite a bit since then, and now it can track multiple people walking around in the room at the same time. And in addition to that, it can reconstruct their full body poses. There's a camera view shown here, but that's only so you can see that the poses that are recovered from the radio signal actually match what you would see with the human eye. There's no camera actually used in reconstructing the poses of the people in this scene. So how does this work? I'm going to give you a little bit of a tutorial on the type of radar that the device uses. At a very high level, though, inside the device, there's an array of transmit antennas. Actually, there's two. There's a horizontal array and a vertical array. And then there's also a set of receive antennas. And when a transmit antenna sends a signal out, it bounces off the person and the signal comes back and the receive antenna picks it up. And The distance to the person is given by the product of the time it took, half the round trip time times the speed of light. And so the question is, how do we figure out how long it took for the signal to travel from the transmit antenna back to the receive antenna? This is a very, very small amount of time because we're operating at the speed of light in a room. So you can't do something like start a clock, wait for something, and then turn the clock off. That would just be a big mess. Instead, the device uses a well-known technique called frequency modulated continuous wave radar. So what does that mean? Well, the transmit antenna sends out a very pure sine wave, but it doesn't send it at a constant frequency. Instead, it sends it at a frequency that grows linearly with time. For example, one of our devices starts at 5.4 gigahertz, and in a very short amount of time, it ramps up the frequency to 7.2 gigahertz. That, by the way, is sort of same ballpark as 5 gigahertz Wi-Fi. So it's the same, we're in the same kind of frequency domain. Okay, so we're transmitting at a frequency that's linearly increasing. And meanwhile, something is coming back and being received later after it bounces off an object in the room. And because the frequency is increasing linearly, the difference in frequency between what you're currently transmitting and what you're receiving tells you how much time elapsed before the reflection returned. And so that's how you can figure out the distance. You just have to know what is the difference between the frequency that is currently being transmitted and the frequency that's being received. And then there's a question of, well, how do you measure that? But that turns out to be a very, very common type of operation that's used in radios all the time, because subtracting a frequency from another is just what you do when you remove a carrier wave from a signal. And it can be done with a device called a mixer. So you feed it in the transmitted signal and the received signal, and it spits out a signal whose frequency is the difference. And then what we do is we compute a DFT or FFT on that difference. And then we look at where are the peaks. And that tells you sort of, okay, those frequencies correspond in a linear fashion to the distances where you're seeing reflections. Now, there's actually more than one transmit-receive pair of antennas. You actually go through all the horizontal antennas and all the vertical antennas, and then you want to combine all their signals to get a complete view of where things are in the room using triangulation or multilateration. You want to sort of say, okay, there's something that's 5 feet in front of me and 2 feet to the right that's reflecting the signal. That's what the aim is. So another way to think about it is you're taking a video, but instead of recording the colors of the objects that light is reflecting off of, you're recording the distances to the objects. So it's a 3D map, but no color, just instead you get distance for each pixel. Okay, so let's talk a little bit about distributed systems. So boy, was it a big mistake to go into the IoT business. You start to realize what a headache it is to have to work in so many different environments. So our device collects a lot of data, and we need to upload that data to the cloud to do more processing, which we'll talk about later in this talk. But how do we do that? Well, we piggyback through the home network, and it turns out that every home user has misconfigured their Wi-Fi network in a different way. So one of our biggest headaches is configuring the device. Once we can get it online, then everything becomes much easier. But getting the device configured is a big problem. Once it's up and running, we do a fair amount of initial signal processing and data compression on the device so that we can reduce the amount of data we have to send upstream. And we can get that down to about 500 kilobits per second to 1 megabit per second. That doesn't sound like a lot, but it turns out that in many homes, this is still difficult to achieve. Upload rates are still a bottleneck in many cases. And it's tempting to think that, well, why don't we just put more processing power in the device and see if we can reduce the data even further? But we actually have a hard constraint on the weight of the device, because we promised the customers, I haven't told you who the customers are yet. They're pharmaceutical companies, and we'll get into why that is. But we promised them we would stick these devices on the wall using 3N command strips and not put any holes in the wall. So the device has to be pretty light, and that limits the amount of compute power you can have in the device. So let's move on now, though, and see why we aren't doing everything in the device. It turns out that we need to do more than signal processing to solve problems like pose estimation. So here's an issue. We have to deal with multipath, which means that when we send a signal from the transmit antenna, it's going to bounce off multiple objects in the room, but it may even bounce in multiple different ways off the same person in the room. And when we look at the signal that we get, we may find multiple peaks that really all correspond to the same person. It's just that the radio waves bounced around the room several times before making it back to the transmit antenna. So how do we extract the human body from this mess? Well, it turns out that what we do after we upload data into the cloud is we use machine learning. And let's look at this one particular problem, estimating pose from these radio frequency signals. What I mean by pose is that we have a very simple model of the human body where there are 14 key body points that are illustrated here. And we want to estimate where each of those points is for a person over a period of time. Now, the first challenge we face is that at any given instant, we're not going to see reflections from much of the body. So we get something that if you look at it, you see a couple parts of the body are reflecting well, and other parts are maybe not reflecting well or not reflecting at all. And the reason for this is that while the human body is a great reflector of radio frequency signals in the Wi-Fi range, like the Silver Surfer there, based on the angle of the surface of the body, the radio signal might bounce back towards the device, or it might bounce in a different direction and we won't capture it. So if you look at the body over time, at any given time, we will see some parts of the body, but not others. And which parts we see will change over time. So if we look at this person walking here, it's meant to show that, like, light, in this case, radio frequency waves, is kind of shining on different parts of the body at different times. You see different things. So in order to recover the pose over the entire period of time, we actually need to process the signal using time as one of the primary dimensions. We can't look at snapshots. We take this three-dimensional data that we've recovered from each snapshot over time, and we feed that into a neural network. And then we want to sort of fill in at any instant where we didn't see a reflection for some part of the body, where we think it was, using the learning algorithm. Okay, this is a big learning problem. It's not an easy one to solve. Now, anytime you try to build a learning model to solve a problem like this, the first question you're confronted is, with is, where do you get the labeled data? And one possibility would be to have subjects wear special equipment that we could detect and use some system to sort of get ground truth data on where the person was. The problem with that is, and there are systems that will do this, but it's hard to capture a large variety of everyday settings, like different kinds of rooms, different people, different obstacles in the room. So you could do that, but that's a hard way to go. You could also try to have humans that label things, and that's possible, but also very time consuming. So what Dina's group did instead was they decided to leverage the fact that there's already mature computer vision technology that can estimate poses from visible light signals, like from video, and to use those systems as a teacher to build the model that would do the same thing using RF signals. The video system is used only as a teacher, though. Once the model is trained, it's not used anymore. So how does this work? So you've got, instead of having some human annotating things, you have a vision model that's taking video and producing these poses, and that's providing ground truth. And then you feed that in along with the radio frequency signals so that you can train a new model that will take in just radio frequency signals and produce pose. This particular system that was used is, by the way, is called Open Pose. Okay, and it provides labeled data, so you can build this other system called RF Pose. And then once it's trained, there's no need for the camera system anymore. Okay, so this is, but by the way, this is kind of a selling point that Emerald makes when it talks to potential users of this system, that there's no actual camera and there's no microphone. Okay, so perhaps that would make you feel that your privacy is more protected. Of course, as you can see, we can still do a lot with the radio frequency signals. We can estimate your pose, but on the other hand, these frequencies are much lower than visible light, so the granularity of an image you could reconstruct is much lower, and we don't get color, and there is no microphone. Another question people ask, though, is, but okay, what about if you didn't care about privacy, wouldn't this all be a lot easier to do with cameras? And the answer to that question is, well, in some cases it might be, but the radio frequency system works in the dark and it works through walls, but maybe most importantly, it can also see through clothes, and it can see through pillows and bed sheets, and we'll see applications where that matters. There are things that are easier to see with radar than they would be with like a visual system. Good. So this is sort of a quirky thing also, that once you've trained the RF system, it can see through walls even though the teacher couldn't. And that's just because the signals penetrate through walls. So the system was trained with about 50 hours worth of data that was generated with OpenPose and recorded at 50 different locations. So it's got a very robust ground truth training set. And here's some demonstrations of how this works. This is after training. The camera is not actually being used here to produce the skeleton. This demonstration is just showing that even if one of the people is walking behind the wall, it's still possible to reconstruct the pose. And this will work even if you have multiple people in the room. And here, I think these are just some graduate students sharing some ideas at the whiteboard. Okay, well, this one is just sort of funny, but you know how Superman has X-ray vision. You can't fool the Emerald device by wearing a baggy sumo costume. It can see through and reconstruct the person's body shape. I will say though, before you get too alarmed, the picture of the person in this video is completely synthetic and not based in any way on the actual person who's being shown. There's just like this library of body shapes, and based on the RF signal, it's picking one and putting it in the right pose. So we're not like generating naked pictures of anybody. Just so you know. So what else can we learn? By the way, those just being able to track people's movements has a lot of interesting applications. And as an example, what we'll see going forward in the talk is that at the moment, the customers for the Emerald service are pharmaceutical companies who are conducting clinical drug trials. And they want to know, is the medication that's being tested effective, or are there any interesting side effects that are being caused by the medication? Or sometimes they're just studying the progression of a disease and they're not even providing a medication yet. They want to know how do patients with this disease, how do they differ from patients who don't have the disease? By being able to track someone's movements, you might be able to answer the question of whether some medication is helping with patients' mobility if they have a neuromuscular disease, for example. So just that capability is helpful in some contexts. But what else can we learn? So the device is capable of detecting the breathing signal very accurately. And this might seem surprising at first because I told you, think about like approximately 6 gigahertz wavelength. That's like a 6 gigahertz frequency. That's about a 5 centimeter wavelength. When you breathe in and out, your chest is not moving 5 centimeters, but you can detect phase change in the reflections, and that's enough. So here, this is Fadil again, actually holding his breath, and while he holds his breath, the signal stops. We have to test that the system works well. We also have these belts that you can wear on your chest, and I've worn one for many nights lying in my bed. And in the morning, we collect the data from the breathing belt and we compare it with the data that we're producing, and we can produce almost identical signals for the two. So without requiring somebody to wear a breathing belt. And in fact, one of the big selling points of this technology is that you don't need to wear anything. And in some cases, that's just a convenience. Like, it's annoying to put on a breathing belt. It's annoying to remember to wear something around your wrist. There are other cases where it's just really not feasible to wear some device. For example, one of the things we do is we can count the number of times that somebody scratches. And if you're testing a drug that treats a dermatological condition, the people in that study probably really don't want to wear anything, right? So that's kind of nice that everything can be done passively. So here's another picture of that breathing signal. I've spent many hours looking at breathing signals and working on the code that extracts them from the images or the videos that we record. You can see, each inhale and exhale here. And if you look really closely, you can actually pick out individual heartbeats. So the device is able to measure a person's breathing, but also their heart rate. It's not really a substitute for a real EKG or something like that. So we don't, not making any claims like that, but You can measure both breathing and heart rates with the device. This is a picture of another one of Dina's students, Mingmin Zhao, who is about to graduate and is going to be, I think, spending some time with us before going on to a faculty position at Penn. And he's in a sleep lab. And when you go to a sleep lab, they put all these sensors on you. And then they ask you to lie in bed and they record electrical signals. I did this once myself, and it was not very comfortable. The worst part was they woke me up at 6 a.m. and told me I had to leave. And I was very eager to hear about the results. And they said, the good news is you don't have a medical problem. You just have a social problem. And that was very deflating. But anyway, this is the standard way that they measure your sleep in a sleep lab. And they this is the Emerald way. So this is another one of Dina's former students, recently got his PhD, Xichao Yu. What these guys did was they figured out how to build a machine learning model that would take the breathing signal and from that extract sleep stages. Like, is the subject awake? Are they sleeping? If sleeping, are they in REM or light sleep or deep sleep? And tricky thing is figuring out how do you measure the accuracy of a system like this? And what they did was they set up a device in the sleep lab at Mass General Hospital. And there are still a bunch of devices there. And there were subjects who were simultaneously being measured by the Emerald device and also by the traditional method that you saw in this picture. And traditionally, after the data is collected, human technicians go and look at it and they hand label the sleep stages. And our results are about in correspondence with the hand labeled data about 80% of the time. You would like that number to be higher, but it turns out that there's, even when you look at different technicians, 80% correspondence is about what you get when you look at the labelings that one technician did versus another. So it's a bit of an art. So this is comparable to hand labeled sleep. I think if you were looking at my slide, it flashed very briefly 1/1000th the power of Wi-Fi, and that's true. So we're sort of roughly in the Wi-Fi range, a little bit above it, but at 1/1000th the power. Okay, let's look at some more applications. So the main application, I mentioned this already, is in-home health monitoring. And we can see things like the difference in mobility between an elderly patient, in this case on the left, and a nurse that comes and cares for that patient. So you can see this patient moves much more slowly. Not a surprise, but that's something you can see. And depending on what you're studying, the rate at which someone can move around may be of interest. Here's an image showing over the course of a day the trajectories that a Parkinson's patient took in their apartment. Like where did they go? This particular patient, it turns out, gets out of bed and spends a lot of the day sitting in that chair right in the center of the image. But you could also do things like measure the number of times the patient went to use the bathroom. That might be of interest, especially if you're studying a disease like Crohn's disease, for example. If we look at that patient and ask, where do they spend their time during a day, you might visualize it using a chart like this. So I call this a tree trunk chart. So each ring is one day. And so this is probably about a month or so. And the first day is the innermost ring. And then we have the different days that follow that. And when the color is blue, that means they're in bed. And when the color is green, they're sitting in that chair. and yellow is a trip to the bathroom. And one thing that is at first glance maybe a little puzzling about this patient is that, well, first of all, their sleep is not so good. It got better during the study. It was really terrible in the first week or two, like very little time spent in bed, although that got better. But even by the end, it looks like they're going to bed around 10:30 p.m. and they're getting up at 3 or 4 a.m. And then they're sitting in the chair until 7 a.m. and then going to the bathroom. And when the physician who is monitoring this patient looked at the chart, he immediately pointed out that what this means is that this patient is not really capable of using the restroom on their own. They're waiting for a nurse to show up at 7 a.m. That's why they're sitting in the chair for that long after they're awake, but yet always go to the bathroom at the same time. So it's kind of like pattern you can see, and there really aren't other methods of collecting this round the clock data that you could visualize and then understand something immediately about what this patient's day-to-day life is like. Yeah, this is another study where patients with Parkinson's disease, perhaps from the same study, were given a medication to help with their mobility, and they take the medication early in the day, and the chart is showing the speed at which they were walking around the room. And after they take the medication, their speed increases, and then it eventually wears off. As a point of comparison, the patient's spouse is shown in red, and the spouse moves much, much more quickly than the patient. Here's analysis of the breathing signal of somebody with sleep apnea, which is a condition where you stop breathing for a while. And this particular subject will just kind of sometimes stop breathing altogether for maybe 30 seconds, which is a sign of, like, pretty serious sleep apnea. So it's not good for you to have this. So if you were to have this detected, you would want to have it treated in some way. So let me go back now to distributed systems. So it occurred to me after working at Emerald for a while that there are some parallels to what I did before at Akamai. That is, that there are ways to view what Emerald's doing as a kind of reverse content delivery network. So first of all, like Akamai and other content delivery networks, Emerald doesn't sell the devices. Instead, it operates a service on behalf of its customers. And the customers are also not the end users. So just as a content delivery network's customers are content providers, in this particular case, the customers are not the people, not the subjects in the home. They're not paying for this. It's pharmaceutical companies that are conducting clinical trials, or we've also been having discussions with insurance and home healthcare companies who would like to monitor their what they say members who have chronic health conditions, to make sure that if something changes in their healthcare status, in their health status, they can be seen as soon as possible. Like, they basically want to avoid a patient's condition deteriorating to the point where they have to go to the emergency room. It's always better when something changes to address it immediately. And then I guess finally a third category are just medical researchers that contract with Emerald to put the devices in the home. So there's that aspect to it, that it's a service and it's operated on behalf of some entity, but not the actual end user. Interestingly, we don't know who the end users are. It's very, very important to us not to know anything personally identifying about the end users. We don't want to know. That causes all sorts of bureaucracy for us. So we don't install the devices ourselves. They're either installed by some third party, or in some cases by the subjects themselves. And there's some identification number attached to the subject and the device, but we don't know who it is, and we don't care. That the pharma company knows that, and they deal with all the red tape, but we don't know who the subjects are. So we, like a content delivery network, we monitor and manage a large number of devices that are deployed in, I say homogeneous devices, that's probably the wrong word, homogeneous environments. The devices themselves are not so homogeneous. They're pretty simple. Like a content delivery network, you're always deploying new servers, and their capabilities will be a little bit different than the year before, but not a lot different. But where you deploy them could be very different. You could be in a data center with a lot of connectivity, or you could be in some campus network, or you could be inside a cellular phone system. And so the networking environment is heterogeneous. Oh, but the devices themselves are homogeneous. So more or less homogeneous. One thing that is nice about doing this in 2021 versus 1998 is that tools for managing and monitoring a fleet of devices are much more mature than they were back in 1998. Akamai had to write everything from scratch. Nowadays, you can just grab open source systems and start with that and modify it, but much more quickly get a pretty reliable system up off the ground for managing and monitoring lots of devices. The biggest difference, though, is that the flow of data is going in the opposite direction. So we're not send very, very little data down to the devices. Occasionally a software update, but not very often. We tend to try to keep the software during the course of one study pretty stable. But we're pulling a lot of data up, and we're doing a lot of interesting processing on the device itself. You might be interested to know that the device itself has a little tiny processor called an NVIDIA Nano, which is about $100 processor. And it's ARM-based, and it runs Ubuntu, and it's got a GPU, but it's really $100 computer. So it's not a very powerful computer. And yet, we're running that thing really hard to do as much as we can on the device to limit how much data we have to send up. But then the data all gets sent up to the cloud, and we happen to mostly use Amazon, and store the data there, and then we run our analytics on the data that's stored in the cloud. And so that's, in some ways, that's like a CDN too, although the CDN analytics tend to be a little simpler. Like I remember the big CDN analytic, at least in the early days, was the billing system, sorting out from all the logs from all the servers, every request that was made to each different customer, and putting those in separate log files and processing them in different ways. Well, sort of similar thing here, except now it's processing the data from the individual subjects. Yeah, so this is Emerald's motto, from wearables to invisibles, and I guess I'm finished a little early. It's hard to judge time sometimes when you're on one of these video calls, but I'd be very, very happy to try to answer questions.
Thank you, Bruce. Very, very interesting talk. I see a combination of smart health, wireless computing, edge computing, cloud computing, machine learning, all in your system. So that's very, very, very interesting. The first, I'm going to take my advantage as a host to ask you, like, is there a plan like you can sort of like, to support like a community research? I believe like many of us are working on like a mobile wireless sensing, cloud computing. And then if like there's like APIs you're going to open, or if there's some, research collaboration opportunities for the community, or something similar.
So I think that that first of all, you're really putting me on the spot with that question, because I'm probably not really allowed to personally make commitments. That would have to go even above my head at Emerald. But we're still a really small company. We're still about 18 people. So there aren't any spare cycles to interface with the research community right now. Having said that, Dina still separately at MIT has a really, productive and high-powered research group. And they're well connected with the research community. One thing that makes this application even more challenging than like the CDN stuff at Akamai in terms of opening up APIs or sharing data or anything is that now you actually have, you can kind of I don't know, people's private health data is very sensitive. So we'd have to have a long discussions about what, if anything, is possible there. Having said that, we don't know who the subjects are either, though. So we face the same issues internally. We just really don't want to know. I've actually see a question that would popped up on the Q&A. So perhaps I could try to answer that.
Yeah. Okay. So device-free health monitoring is very interesting and user-friendly. However, do we also measure the implications of what a signal has been absorbed by human body, especially special cases like a pregnancy?
Yeah, and of course I 100% agree. You don't want to deploy a device that might have negative health impacts on anybody. But as I mentioned during the talk, we're using radio frequency signals in the same frequency range as Wi-Fi, but at 1/1000th the power. So the incremental amount of electromagnetic radiation over somebody who's got Wi-Fi in their home is negligible. So I think in this particular case, that the scientific consensus is that Wi-Fi signals are not harmful to your health, even during pregnancy. I'm not an expert, but I understand that's a consensus. And so this particular device shouldn't be either.
Thank you, Bruce. I see Dama, please go ahead.
Hi, Bruce. Thank you for the talk. Mine is not a technical question. So for me, it is about how do we attract more people to systems research, distributed systems, networking, operating systems, whatever. So let me put in context. I think if I were a grad student today, I personally would be so motivated to make people's lives better directly that I would end up working in the many research areas in computing that are closer to actually, touching people, making a difference, like the project that you're doing now. I think, but also, of course, I know that we need people in computing in other areas. So I'd like to see if you have any ideas on how can I keep selling, in particular for women and people from underrepresented populations, which studies indicate that they are really motivated sometimes for social good and things like that. So how do I sell them systems? So I heard your talk and I can see large scale. I can tell people we need to really know how to do things large scale, otherwise we leave people behind. But I wonder if you do have, based on the experience that you're having now, working a little closer to making my mom's life better. What can we do to keep more people coming to graduate school in systems, even though, we get so many papers rejected and maybe other groups in other areas, their friends that they have lunch, have so many more papers accepted. So any thoughts on all of this?
Well, and first thought is I realize I'm part of the problem because here I'm a systems person, but I'm getting to show videos of kind of, futuristic machine learning applications recovering people's body poses from microwaves. And that just seems really cool. But the reality is, if you look at the engineering team at Emerald, 2/3 of it is systems people who are making this all really work. And that is a hard thing to convey, maybe, that there's sort of this whole system requirement to make any progress. It can't. You might think that because you have a clever algorithm or you've come up with you know a new approach that you know everything else is easy, but that's not true, right? Systems is what we build the platforms that enable us to scale these new technologies. And when we do that, we run into new challenges that are completely different than anything we ever saw before, and require solving, you know, new systems problems. You know, having said that, you're right though. Systems is a very mature field in some sense, because people have been doing systems work since the 60s, and the systems community tends to be a little conservative, and it's really hard to convince them that you've made a pure systems contribution that's you know, that's worthy of respect. And it's sort of easier to work in an area where everything's brand new. So I think that and of course, you know, I'm just answering off the top of my head, but I think that the main thing is that nothing works without systems. You know, and there are always new system challenges anytime you have a new application. I don't know if that's
that helps. You know, I'm trying to put together a lecture or a keynote exactly about this. So I think your talk really, you know, helped me in general in your answers too. Thank you.
Thank you, Bruce. There's another question in the Q&A from Lucy. Is there real-time processing for possible actions, or most of the activities are for collecting the data and analyze them later?
Yeah. So, well, at the moment, there's no real-time requirement. That is that, or there's no real-time offering. But some of these things can be done in real time. So, for example, we can collect a breathing signal or a heartbeats in real time. We're not being asked to do that. We did some little experiments where one of the hospitals wanted to see if they could have, when COVID first started, could they put a device in the emergency room and remotely look at people's breathing without having to go too close to them. And so we don't actually have a product that does that, but we demonstrated that we can do that. So I think that's a little further down the road. Obviously, there are some applications where it'd be nice to know if something has changed in real time.
Thank you, Bruce. Abhishek, I see your hands on.
Sure. Yeah, hi, Bruce. Thanks for a really good talk. And this is really cool technology. So one concern I was thinking about, and you mentioned this a little bit, was sort of privacy issues. And in some sense, this is a little bit even more intrusive because the user may not even be aware that there's this device sitting maybe on the other side of the wall. And even while we are probably monitoring a patient in their house, but maybe there are other people who are visiting them whose movements are also potentially being recorded. So one question more specifically was, how do you take care of these kind of privacy concerns in this context? But I also wanted to broaden this out more. We have been having a lot of discussions in our department about ethics of computing and sort of teaching students about how to consider the implications of whatever code they are writing or products they're developing and so on. Can you also talk more broadly in those terms, like, are there these kind of concerns that you guys discussed, or how do you deal with these kind of issues as you're developing these technologies and products?
Yeah, absolutely. So, you know, first of all, at the moment, the subjects are allowing the device to be deployed voluntarily, and they're giving a full briefing on this. And they generally are highly motivated because they want to participate in the study, for example. But there's still the issue about what about other people in the same home. So I didn't really talk about this, but one of the things that we can do is differentiate between the subject who we care about and other people in the home. And the way that that's done is that in the very early days of the deployment, right after the device is deployed in the home, the subject wears an ankle band that's got an accelerometer in it. And so we were able to track the subject and build a model so that we can distinguish that subject from anybody else. And once we can do that, we can throw away all the data from everybody else. In addition to that, when the device is deployed, we map out the shape of the apartment or the house, and we throw away all the data that goes outside of the boundaries of the room or the rooms that are being monitored. So I guess that's about all I can say. There's active consent, and then there's an effort to make sure we don't collect data from non-subjects. Oftentimes the measurement is also really pretty specific. It's the pharmaceutical company wants to measure the person's breathing at night in bed, and we know which side of the bed the person sleeps on. And so, we have no interest in collecting data from anybody other than the subject, because that just makes us look bad. So we really try our hardest to just get the data from the subject, and we don't even know who the subject or who anyone else in the room is anyway. I see another related question about, what if this technology was more widespread, and what if somebody used it to, monitor me in my house from outside the house? And I think that is, from a technological perspective, that is a real concern. I guess, and that can already be done. People can already use cameras, microphones, infrared cameras, and in fact, there are microwave. So we are really specializing in the health applications, but we didn't invent, FMCW radar. People have had radar that could see through walls and pick up images of people before MIT and Emerald started this project. So yeah, that's the technology in various forms is there and probably will just become more widely available. And I think this is one of these things that has to be addressed in different ways by having rules that say, you cannot do this. You can't invade someone's privacy that way. But it's a good question.
Yes, thank you, Bruce. I see Fan also has questions. Fan, can you unmute yourself?
Yes, Bruce, really fascinating talk. Enjoyed it very much. One question I have is probably a more technical one. Some of the problems we find in this radio-based sensing is real life environment, and the radio signals are far more complex and noisy as compared to some of the controlled lab environment. So the real signals tend to be much more messy compared to some of the examples we have seen. So I wonder, when you really deploy these in people's homes, what about the robustness against different kind of home environment, different people's body build? For example, there are people who are larger versus smaller, and clothing would also change, summer versus winter, right? And then sometimes there are pets running around. So I think in general, real life environment and signals are far more complicated as compared to, let's say, 50 hours of training data collected in a lab environment. So how do we approach these kind of issues? Is it just more data, more training, or algorithm-wise, there are actually ways that can that can help overcome some of these real-life challenges?
Yeah, so you're absolutely right. We keep running into things we never would have expected in the home that cause great complications for us. One thing to be clear, though, that like the 50 hours of training was not in the lab. That was all over campus. It was in many different places. But nevertheless, there are things that cause trouble. So one thing I didn't mention is fans, like, are a real pain. There's some fans sitting there in the room, and it's generating harmonics that are just at the breathing cycle of a person.
Right.
Fans really stink. And then our radio overlaps Wi-Fi a little bit, and if they're on the wrong channel, from our perspective, we've got to deal with interference from the Wi-Fi. And pets, if the pet sleeps in the bed, okay, so that's a big hassle too, because we're trying to pick up this person's breathing signal and there's this dog going in the bed. So, I mean, a lot of what we do though is we try to control the environment. So we say, if we tell the pharmaceutical company, don't put the device in a home where the pet sleeps in the bed, or they don't have Wi-Fi. And if they do have Wi-Fi, if they're on channel 157, we switch them to some other channel. In general, and if there's a fan, what we do is we find the fan, we learn where that fan is, and then we cut it out of the data. So, but you're absolutely right. It's every home environment poses new challenges, and I think that we're not trying to do everything. We're usually trying to do one or two things well, like get this person's breathing and sleep data at night, or their mobility data in the living room. And so, it becomes workable and reasonably robust. I mean, we've deployed hundreds of these devices. We're successfully collecting data on each one for maybe 3 to 6 months. So we're starting to get a feel for how to work around these common problems.
Okay, thank you. Great insights.
Thank you, Bruce. That's why I asked my first question that, there might be like a space that the community can also help to attack some of those challenges, and then eventually maybe like the company will be able to incorporate more functions, like more activities or more diseases, like those kind of things. If there's opportunity for the community to like collaborate. Yeah, sorry, I put you into the hot spot, but I think it's really a fantastic talk, and I enjoyed it so much. I really appreciate that you got up so early in the morning. It's like 6 a.m. right now. I can see from back of your background.
The sun has come out.
No, it's still early morning, from the very early morning to the early morning. And we really appreciate your time, and thank you very much. And I think we'll learn a lot from you, from your talk, and we look forward to the success of the Emerald innovations. And for this, by the way, I recall that like 20 years ago, 20 years ago at ICDZ 2001. One of the keynote was given by the VP of engineering of Google at that time. Okay, so 20 years later, Google grows so big, and you are the director of engineer at Emerald Innovations, and we expect like 20 years later, you were on parallel to Google. Yeah.
Okay, so thanks for the sentiments. I don't want to make comparisons to Google, but I also don't want to wait 20 years.
Okay, sorry. Thank you.
Okay, thank you very much. Thanks again for inviting me. Aloha to everybody.
Thank you so much.
Bye-bye.
Bye.